Okay, we do one more example. For example, if we are calculating the derivative of y equals to x power 3 using definition. By definition, we mean the first principle or with the help of difference quotient. So we take y equals to f of x equals to x cubed. I need f of x plus h as well. So that will be x plus h whole cubed. If we expand this cube, we will have x cubed plus 3x square h plus 3x h square plus h cubed. If you don't know it, just google the identity of a plus b whole cube. You will know how to do this. Now for difference quotient, we have to subtract f of x from f of x plus h and divide it with h. So I put the value of f of x plus h here, and I put the value of f of x. So this x cube and x cube get cancelled. Now the difference quotient is 3x square h plus 3x h squared plus h cubed divided by h. We see h is common in every term, so we factor out h in the next step. Now from this term, h get eliminated, so I have 3x squared. From this term, it was h squared, so one h went out as a factor. The other h is written here. H time h will be h squared again, and from h cube I'm left with h squared because I factor out h previously, right? Now this h of divide and multiply will cancel each other, so the difference quotient now will be equal to 3x squared plus 3xh plus h squared. The difference quotient give the slope of secant line, that's average change. We need derivative, which is instantaneous change. So we apply h goes to 0 limit. We apply limit on the difference quotient, so that converts into derivative. If I apply limit here, this term is independent of h, so nothing would happen to that. This one has h, so if h goes to 0, the entire term goes to 0. This one is h squared, so if h goes to 0, this goes to 0. I get rid of these two terms. I'm left with 3x squared only. So the derivative of x cubed with respect to x is 3x squared. We recall. Before recall, let me give you the idea how it looks on the graph. So if I have a graph of x cubed, it looks like this, the blue line that you see. If I draw all the tangents on it, you see only at 0 the tangent slope is 0, right? So if I put 0 here, it will be 3 times 0 is 0, right? So this is aligned. The rest of the slopes all are positive. Every line looks like this, it has a positive slope. So even if you put negative values of x, your slope is positive. If you put positive values of x, your slope is still positive, it's not changing. So that means this x square will never give you a negative answer, obviously. So the slope would always stay positive. Now this derivative and all these slopes, they are in sync with each other. That means we have calculated the right derivative. Now if we recall, in the previous video, the derivative of x square was 2x. So that means there is a pattern if we look at. So if it is x cubed, the power comes in multiply and the original power is reduced by 1. So the next term is x squared rather than x cubed. If it was x square, the power came in multiply and the original power 2 is reduced by 1. So I have 2 times x power 1 now. So if that is the pattern, the derivative of x power 4 should be 4x power 3. So that way we come up with a rule which we call power rule. It says that if you find the derivative of any power function means x power n. So if you have x power n and you find the derivative of it with respect to x, the original power will come down in the multiply. The former power, the previous power n, will now be subtracted by 1. So the new power will be n minus 1. So if you are finding the derivative of x power 1000, it should look like 1000 times x power 999. Or if you have a reciprocal function which is 1 over x, if you want to find the derivative of 1 over x, 1 over x can be written as x power minus 1. So the original power is minus 1. You take minus 1 and multiply and reduce minus 1 by 1 again. So minus 1 subtracted by 1 will be minus 2. So you will have minus 1 times x power minus 2. That will be 1 over minus 1 over x power 2. If you bring x power minus 2 in the denominator, the power will shift into positive, so you will have minus 1 over x square. The derivative of 1 over x will be minus 1 over x square. So in this short tutorial we learned to find the derivative of y equals to x cubed by definition. That gave us a pattern that whenever you use a power function, the derivative of a power function will be bring the power down and reduce the power by 1. So that's how it works. Let's discuss some of the derivatives to understand this pattern or understand the power rule. So we said the derivative of x power n will be n times x power n minus 1. The original power will get into multiply. The new power will be the old power minus 1. So for example, x power 100 will be 100 times x power 99 if you take the derivative of it with respect to x. Now we discuss the derivative of square root of x. So we know the square root of x is the same thing as x power 1 upon 2 or x power half. So that means this half will come in multiply and the new power will be x power 1 upon 2 minus 1. So if you subtract 1 from 1 upon 2, you will have negative half. So 1 upon 2 x power negative half. If you bring the x power negative half in denominator, you will have x power positive half because the negative power will convert into positive power. You know this basic property of the exponential numbers. So 1 upon 2 times 1 upon x power half. 1 upon x power half can also be written as 1 upon the square root of x. So the multiplication of this will be 1 upon 2 times the square root of x. So now we know the derivative of square root of x with respect to x will be 1 upon 2 square root of x. We do the derivative of x power minus 2 as well. That will become minus 2 times x power minus 3. If we do the derivative of x power negative half with respect to x, we will have negative half in multiply x power negative half minus 1. So if you subtract 1 from negative half, you will have negative 3 by 2. So the total derivative will be negative half times x power negative 3 by 2. Now we discuss the small things that we did in the introductory lecture, that if I find the derivative of x with respect to x, so x got 1 power, so 1 will get in multiply x power 1 minus 1. X power 1 minus 1 is 0, so I will have 1 times x power 0. Any number other than 0, if it is raised to power 0, it becomes 1. So x power 0 is 1, 1 times 1 is 1. So the derivative of x with respect to x will be 1. The derivative of y with respect to y will be 1. The derivative of any variable with respect to the same variable will be 1. This so we are not discussing the derivative of constant right now. We'll do that in a moment. We discussed some of the important properties. For now we are discussing the sum and the difference property. We say if you apply derivative to the sum of two functions, it will be the same as the sum of two derivatives of the functions. So you apply derivative to the f function first and to the g function, then add the answers of these two derivatives. It's the same thing as if you do the sum first and then apply the derivative. Or if you are applying derivative to the difference of two functions and you take the derivative of both functions first, then take the difference of these derivatives both ways, you can get the same answer. So we take the derivative of x cubed plus x square. We consider x cubed to be one function and x square to be another function. We will have to find the derivative of x cubed separately and the derivative of x square separately, and then the two derivatives will be subtracted from each other. So the derivative of x cubed is 3x squared and the derivative of x squared is 2x. We sum them. Sorry, I mistakenly said difference instead of sum in this part. The similar way, if I consider two functions x power minus 1 and take a difference of that with x power 4, I'll have to take the derivative of x power minus 1 first and then subtract the derivative of x power 4 from that. The derivative of x power minus 1 will be minus 1 x power minus 2, or I can simplify it to be minus 1 divided by x power plus 2, minus the derivative of x power 4 is 4x power 3. So that's how it works. You want the derivative of a sum, you just take the derivative and then sum the results. You want the derivative of difference, you take the derivative and then have the difference of the answers. It works like that. 1. Another important property of finding derivative is the constant multiple property. If we need to find the derivative of a function that is multiplied with some constant number 2, 3 or negative 2 or negative 3, it will be the same thing if you find the derivative first and then multiply it with the same constant. For example, if you need to find the derivative of 4 multiplied with x power 3, you take the 4 out, find the derivative of x power 3 first, and then multiply them. So the derivative of x power 3 is 3x squared. You multiply it with 4, you get 12x squared. Now this way we can make sense of the derivative of the constant as well. If I need to find the derivative of any constant number, say 4, 5 or negative 4 or 0 or something, we have discussed this in the concept video that the derivative of a constant is 0 because constant gets no change no matter what happens. So I can write it like the derivative of constant times x power 0. Now I'm considering x power 0 to be my function, and that function is multiplied with some constant. This property dictates that take the constant out and find the derivative of the function. Now by writing it this way, I have made no changes at all because x power 0 is 1. 1 times any number would be the same number, right? So if I find the derivative of x power 0 using power rule, the 0 will get into multiply. No matter what happens to the x, if it gets multiplied with 0, it's 0. Then you multiply 0 with k, everything is 0. So the derivative of the constant is 0. That works. Next, now if we discuss an example and use all the properties that we have discussed so far, we have y equals to x power 9 minus 6 times x power 5 plus 7 times x minus 11, and we need the derivative of this. So we apply the sum and the difference principle first, that if two functions are getting subtracted from each other, find their derivative and then subtract. If two functions are getting added with each other, find their derivatives respectively and then add them, and so on and so forth. So that means we will apply derivative to every term individually. I apply derivative to x power 9, that's 9 times x power 8. I apply derivative to 6x power 5, keep this minus same. So this is a constant multiplied with a function. So I take this 6 out and needs to find the derivative of x power 5 first. Then the derivative of 7x, 7 is a constant multiplied with a variable. So I bring 7 out in the multiply and find the derivative of x, minus the derivative of 11. 11 is a constant. The derivative of constant is 0. So the derivative of 11 is 0. So 9 times x power 8 stays same, minus 6 stays the same. The derivative of x power 5 is 5x power 4. We know by power rule. 7 stays same. The derivative of x is 1, again by power rule. So 9x power 8 minus 6 times 5 is 30. So that's 30x power 4 and plus 7. So in your exercise, you have a lot of questions which are these algebraic equations or polynomials. You need to find their derivatives. From exercise 3.1 onwards, you will have to find the derivatives this way directly, not by the definition principle or so on and so forth. In exercise 2.7 and 2.8, you need to use the difference quotient and the definition approach, but from 3.1 onwards, you need to do this stuff.